What if everything you thought you knew about reality was just the tip of the cosmic iceberg? Picture the most extreme environment in the universe, a place where gravity becomes so powerful that not even light can escape, where time doesn't just slow down but twists into knots, and where the very fabric of space tears open like a curtain revealing backstage to existence itself. Black holes aren't just celestial oddities. They're the universe's best-kept secrets, holding clues to mysteries that could rewrite the rules of physics as we know them. And today, we're venturing beyond the event horizon to uncover 26 astonishing theories about the hidden realms lurking within these cosmic enigmas. Ideas so revolutionary, they blur the line between science and the fantastical. Think about the last time you stared up at the night sky, wondering what lies beyond those pinpricks of light. Now imagine discovering that some of those distant stars might actually be portals, doorways to other dimensions, alternate timelines, or even entirely new universes. That's exactly what some of the boldest theories about black holes suggest. These aren't just destructive voids sucking everything into oblivion. They could be cosmic architects, shaping realities we can't even begin to fathom. From wormholes threading through space-time like subway tunnels between worlds, to holographic universes where our three-dimensional existence is merely a projection on a two-dimensional surface, black holes might hold the keys to understanding it all. But here's what's truly mind-blowing. Every one of these theories is grounded in real science, backed by equations scribbled on blackboards by the brightest minds of our time. This isn't speculation, it's the frontier of human knowledge, where the wildest ideas often turn out to be true. So if you've ever felt the itch to explore the unknown, to peer into the abyss and see what stares back, you're in the right place. By the time we're done, you'll never look at a black hole the same way again. Are they the end of everything or the beginning of something far stranger? Strap in, we're about to find out. Let's start with the first hidden realm, the Einstein-Rosen bridge, better known as a wormhole. Picture a cosmic shortcut, a tunnel stitching together two distant points in spacetime like folding a piece of paper and poking a hole through it. Einstein's own equations hinted at this possibility, suggesting that the intense gravity of a black hole could warp space so severely that it opens a passage to another place, another time, or even another universe entirely. But here's the catch: these bridges are notoriously unstable. They'd snap shut faster than you could say, interstellar road trip, crushing anything daring enough to enter. That's where exotic matter comes in, a hypothetical substance with negative energy that could prop the wormhole open long enough for a spacecraft or even information to slip through. Now imagine the implications. A traversable wormhole could turn a journey of billions of light years into a stroll across the cosmic backyard, colonizing distant galaxies, meeting alien civilizations, or even sending messages across time. All of it becomes tantalizingly possible. But don't pack your bags just yet. The biggest hurdle: we've never found exotic matter, and no one knows if it even exists outside of theory. Still, the math checks out, and that's enough to keep physicists dreaming. Some speculate that advanced civilizations might have already mastered wormhole travel, using black holes as secret transit hubs. Others warn that tampering with spacetime could unleash catastrophic paradoxes, like accidentally erasing your own past. The wildest part: wormholes might not just connect places, they could link entire realities. If our universe is just one bubble in an infinite cosmic foam, black holes might be the threads tying it all together. Every time you peer into the abyss, you're not just looking at a void, you might be staring at a gateway to everything else. But what if black holes aren't just one-way streets into oblivion? Enter the white hole, a cosmic geyser blasting matter and energy outward instead of pulling it in. Picture a black hole's mirror image, where the relentless gravity that once trapped everything suddenly reverses, hurling stardust back into the cosmos like a celestial eruption. Some theories suggest these white holes might be the hidden escape routes from black holes, a secret backdoor where everything swallowed by the abyss gets spit out somewhere else entirely. Here's where it gets even wilder. If a black hole in our universe connects to a white hole in another, it could mean that nothing truly vanishes, it just relocates. A star torn apart in our corner of space-time might re-emerge as a fountain of energy in a distant reality, rewriting the rules of cosmic destruction. This isn't just science fiction. Einstein's equations allow for white holes, though we've never observed one. Some physicists speculate they could be incredibly rare, flickering into existence for mere moments before collapsing back into the fabric of space-time. Others think they might be hiding in plain sight, masquerading as mysterious cosmic explosions we've yet to fully understand. Consider gamma-ray bursts, some of the most energetic events in the universe. What if these aren't just collapsing stars or colliding neutron stars, but the violent birth cries of white holes? The math suggests that a white hole's eruption would release staggering amounts of radiation, eerily similar to what we've detected from these deep space phenomena. And if that's true, it would mean we've been witnessing the aftermath of black holes all along without even realizing it. Yet the biggest question remains, where does all that ejected matter go? If white holes are real, they might not just bridge universes, they could be recycling cosmic material on an unimaginable scale. One theory even proposes that our own Big Bang was the explosive finale of a white hole in a previous universe, turning the ultimate end into a breathtaking beginning. It's a dizzying thought. Every black hole could be sowing the seeds of a new reality, turning destruction into creation on a scale we're only starting to grasp. So the next time you hear about a black hole's insatiable hunger, remember, it might not be the end of the story. Somewhere in a universe we can't yet see, there could be a white hole lighting up the darkness, proving that even in the cosmos, nothing is ever truly lost. What if the three-dimensional world around you, the solidity of your chair, the depth of the night sky, even the sensation of time passing, was nothing more than an elaborate illusion? This isn't the plot of a sci-fi movie. It's the heart of the holographic principle, one of the most radical ideas to emerge from black hole physics. Imagine the event horizon of a black hole not as a one-way ticket to oblivion, but as a cosmic projector screen, encoding every bit of information that falls inside it. Like a hologram where a two-dimensional surface creates the illusion of depth, the universe itself might be a vast, hyper-realistic projection, with black holes serving as the ultimate data storage devices. The math behind this is as elegant as it is bizarre. When matter vanishes into a black hole, it doesn't just disappear, it leaves an imprint on the event horizon, a kind of quantum tattoo etched into the fabric of space-time. Think of it like burning a book. The pages are gone, but the smoke and ash still carry traces of the words. In the same way, a black hole's surface could hold the complete blueprint of everything it's ever consumed. This revelation led physicists to a staggering conclusion. If the information inside a black hole can be perfectly preserved on its boundary, maybe the entire universe operates the same way. Our perception of three-dimensional space, with its galaxies, planets, and people, might just be a holographic reconstruction of data stored on a distant, two-dimensional surface. But how could this possibly work? Picture a video game where every blade of grass, every ripple of water, is generated in real time from lines of code. Now scale that up to cosmic proportions. The holographic principle suggests that the universe is the ultimate simulation, with black holes acting as the servers storing the raw data. Even stranger, this could mean that time itself is an emergent property, not a fundamental feature of reality, a side effect of how the cosmic code is rendered. It's an idea so counterintuitive that even Einstein might have balked, yet it's grounded in cutting-edge physics, from string theory to quantum gravity. The implications are dizzying. If the holographic principle is true, then black holes aren't just cosmic vacuum cleaners. They're the universe's librarians, cataloging reality in a language we're only beginning to decipher. Some researchers speculate that this could solve one of physics' biggest headaches, the black hole information paradox, which pits quantum mechanics against general relativity. If information is never truly lost, just transformed, it would mean the universe has a built-in backup system with black holes as its hard drives. And here's the real kicker: this might not just apply to black holes. If the holographic principle holds, our entire universe could be a shadow cast by processes happening on a distant, two-dimensional boundary we can't see or touch. The chair you're sitting on, the device in your hand, even your thoughts, all of it might be the three-dimensional echo of data written on the edge of existence. It's a humbling thought, one that makes the line between science and philosophy blur. Are we living in a universe, or are we part of a cosmic hologram with black holes as the projectors? The answer might be hiding just beyond the event horizon, waiting to rewrite everything we know about reality. Time doesn't just slow down near a black hole. It can twist into knots so tangled that the past, present, and future might loop back on themselves like a Möbius strip of reality. This is the realm of closed timelike curves, where gravity warps time so severely that a particle could theoretically complete a journey that brings it right back to where and when it started. Picture throwing a rock into a river, only to watch it circle back upstream and land in your hand again. That's the kind of temporal chaos black holes might unleash, turning cause and effect into a cosmic game of ping-pong. Einstein's equations hinted at this possibility, showing how extreme gravity could bend time into a closed loop where events repeat endlessly. Imagine stepping into a black hole and witnessing your own birth, or worse, becoming your own ancestor. The paradoxes pile up faster than stardust near the singularity, but here's where it gets even stranger. Some physicists argue these loops aren't bugs in the universe's code, they could be features. If closed time-like curves exist, they might act as nature's way of preserving information, recycling it through time like a cosmic backup drive. Yet the universe seems to have safeguards against such chaos. The Novikov self-consistency principle suggests that any time travel within these loops would only play out in ways that avoid paradoxes. You couldn't go back and prevent your own birth, for example, because the timeline would somehow correct itself, forcing events to unfold as they always have. It's as if reality has an invisible editor snipping out contradictions before they can unravel the fabric of causality. But black holes might not just bend time, they could shatter it entirely. Near the singularity, where gravity becomes infinite, our understanding of physics breaks down. Time might not just loop, it could fracture into fragments, with each piece representing a parallel timeline. Some theories propose that what we perceive as the end of time inside a black hole is actually a branching point, where every possible outcome spins off into its own universe. One moment you're falling toward oblivion, the next you're scattered across a multiverse of alternate fates. The real question isn't just whether black holes create time loops, but what happens to anything or anyone caught in them. Are these cycles eternal prisons, trapping matter and energy in endless reruns? or could they be gateways to eras long past or futures yet to unfold? The answers might lie hidden beyond the singularity, in a place where time itself loses all meaning. Until we can peer past that boundary, one thing's certain: black holes don't just warp space, they turn the clock into a plaything, proving that even time isn't safe from their gravitational grip. Beneath the crushing weight of a black hole's gravity, past the point where even atoms are ripped apart, lies a realm so bizarre that our laws of physics crumble into chaos. This is the quantum foam singularity, a place where space-time doesn't just bend or tear, but bubbles and froths like a boiling ocean of reality itself. Forget the classic image of a single, infinitely dense point. Here, the very fabric of existence dissolves into a seething foam of microscopic universes, each popping in and out of existence faster than a heartbeat. Imagine trying to walk across a floor made of bubbles. One moment you're standing on something solid, the next you're plunging into nothingness. That's the nightmare landscape waiting at the heart of a black hole, where space and time cease to behave in any recognizable way. This isn't just poetic speculation. Quantum mechanics tells us that empty space is never truly empty. It's a turbulent sea of virtual particles flickering in and out of existence. Now amplify that turbulence to cosmic extremes, where gravity warps space-time so violently that even this quantum froth is stretched and shredded. The result: a singularity that's less a point and more a writhing, dynamic swarm of space-time bubbles, each a tiny universe with its own fleeting rules. Some physicists compare it to the foam on a cappuccino, seemingly smooth from a distance, but up close, a chaotic dance of fleeting structures. The implications are staggering. If the singularity isn't a single, infinitely dense pit but a frothing quantum whirlpool, it could rewrite our understanding of black holes entirely. Maybe they don't end in destruction but transform, recycling matter and energy into new configurations we can't yet comprehend. Picture a cosmic kaleidoscope where every twist of gravity creates new patterns in the foam, some collapsing instantly, others budding off into pocket universes. This could explain why black holes seem to vanish over eons, slowly evaporating through Hawking radiation. They're not leaking energy, they're dissolving back into the quantum froth they came from, their singularities unraveling like sandcastles in a tidal wave. But here's the real mind bender. If space-time is foamy at the smallest scales, could this quantum chaos be the true foundation of reality? Some theories suggest that what we perceive as the smooth, continuous universe is just an illusion, a statistical average of trillions of quantum bubbles too tiny and short-lived to notice. Black holes might be the only places where this underlying froth is magnified to visible extremes, like cosmic microscopes revealing the universe's pixelated underbelly. It's a humbling thought. The vast galaxies and empty voids we see could all be riding atop a seething quantum ocean, with black holes as the whirlpools that occasionally pull back the curtain. Yet for all its strangeness, the quantum foam singularity might hold the key to unifying physics' greatest rival theories: general relativity and quantum mechanics. Relativity paints gravity as the smooth curvature of spacetime, while quantum mechanics deals in discrete, jumpy particles. In the foam, these two worlds collide. Gravity becomes quantized, spacetime granular. It's as if the universe is trying to reconcile its own contradictions in the only place extreme enough to force them together. If we could peer past the event horizon and map this foam, we might finally crack the code of quantum gravity, unlocking secrets that apply far beyond black holes. So the next time you think of a singularity, don't picture a static dot of infinite density. Imagine a living, breathing quantum storm, a place where the universe reinvents itself moment by moment, and where the answers to our biggest questions might be hiding in the foam. Crossing the event horizon of a black hole should feel like drifting into a silent abyss, at least according to Einstein. His equations paint it as an uneventful boundary, where gravity's pull becomes inescapable but nothing drastic happens to you at first. But what if that's dangerously wrong? Imagine approaching the edge of a black hole, expecting to slip smoothly into the darkness, only to hit a searing wall of energy hotter than the core of a star, a cosmic shredder that vaporizes everything in an instant. This is the Firewall Paradox, a theory so radical it's forced physicists to question whether we've misunderstood black holes entirely. The problem starts with a clash between two pillars of physics, general relativity and quantum mechanics. Relativity says the event horizon should be uneventful, a point of no return but not a physical barrier. Quantum mechanics, though, suggests something far more violent. When matter falls toward a black hole, it radiates energy, a phenomenon called Hawking radiation. Over time, this radiation causes black holes to evaporate, raising a critical question. What happens to all the information swallowed by the black hole? Quantum rules say information can't be destroyed, but if it's trapped inside an evaporating black hole, where does it go? Enter the firewall. Some physicists argue that the only way to preserve quantum consistency is if the information never makes it inside the black hole at all. Instead, it's incinerated at the event horizon, transformed into a furious storm of high-energy particles. Picture throwing a book into a furnace. The pages burn, but the ash still holds traces of the words. In this case, the firewall acts like that furnace, encoding information into the radiation blasting outward. It's a brutal solution to the information paradox, but it comes at a cost. Einstein's smooth, uneventful horizon gets replaced by a literal wall of fire. The implications are staggering. If firewalls exist, they'd mean black holes aren't just gravitational traps, they're cosmic shredders, annihilating everything that comes near. A spacecraft crossing the horizon wouldn't experience the infamous spaghettification from tidal forces. It'd be reduced to plasma in nanoseconds. Even stranger, firewalls challenge the very notion of what an event horizon is. Instead of a passive boundary, it becomes an active participant, a place where the laws of physics rewrite themselves in real time, but not everyone's convinced. Critics argue firewalls violate the equivalence principle, a cornerstone of general relativity stating that free-falling observers shouldn't feel extreme forces. If you're plummeting toward a black hole, you shouldn't notice anything unusual at the horizon. No fire, no drama. The fact that firewalls break this rule suggests our theories might be missing something fundamental. Could quantum gravity, the elusive theory bridging relativity and quantum mechanics, resolve the contradiction? Or is the firewall a red flag, signaling that black holes are even weirder than we thought? One alternative suggests the paradox isn't about firewalls at all. It's about how we define the horizon itself. Some models propose that the event horizon isn't a static boundary, but a dynamic, quantum fuzzy region where space and time fluctuate wildly. In this view, the firewall isn't a permanent structure but a fleeting effect, like a wave cresting before it crashes. Information might not burn up instantly, but could be scrambled and ejected over time, like a cosmic puzzle reassembling itself in the radiation. The debate rages on with no clear winner yet, but the firewall paradox does something remarkable. It turns black holes from cosmic vacuum cleaners into laboratories for testing the limits of physics. Every time we think we've got them figured out, they throw another curveball, forcing us to dig deeper. Whether the firewall is real or just a signpost pointing toward deeper truths, one thing's certain: black holes refuse to play by the rules we've written for them. And that's what makes them the most fascinating puzzles in the universe. What if every black hole is a cosmic womb giving birth to an entirely new universe? This mind-bending idea suggests that when matter collapses into a singularity, it doesn't just vanish, it erupts into a fresh reality, complete with its own laws of physics. Picture the moment of the Big Bang, an unfathomable concentration of energy bursting outward, creating space and time from nothingness. Now imagine that same process happening inside a black hole, hidden behind its event horizon like a secret pocket of creation. The equations of general relativity actually allow for this possibility, showing how the extreme curvature of spacetime near a singularity could trigger a rebound, a cosmic springboard launching a new universe into existence. Think of it like a Russian nesting doll where each layer hides another world inside. The black holes in our universe might contain infant cosmoses of their own, each with stars, galaxies, and perhaps even life, all unfolding in dimensions we can't perceive. Some theories propose these baby universes inherit slight variations in physical constants from their parent, meaning gravity, light, or even time could behave differently there. One might have stars that burn 1,000 times slower. Another could be so densely packed that planets form in hours. It's a staggering thought our own universe's finely tuned laws, which made life possible, might just be one random roll of the cosmic dice in an endless chain of black hole births. But how could we ever prove this? The event horizon acts as an impenetrable curtain, shielding any internal expansion from our view, yet subtle clues might linger. If our universe was born this way, it could carry faint imprints of its parent's demise, anisotropies in the cosmic microwave background, or peculiar gravitational waves echoing from the dawn of time. Some researchers even speculate that dark energy, the mysterious force accelerating our universe's expansion, could be the residual energy of that primordial black hole collapse, like an umbilical cord still pulsing with power. The most profound implication isn't just the existence of baby universes, it's the possibility that we're living inside one. If black holes spawn new realities, then our entire cosmos might owe its existence to a singularity in some long-forgotten ancestor universe. Every star, every planet, every one of us could be the aftermath of another world's gravitational collapse. This turns the life cycle of the cosmos into an infinite loop, universes giving birth to black holes which birth new universes ad infinitum. Destruction becomes creation, endings become beginnings, and black holes transform from cosmic graveyards into the most fertile places in existence. So the next time you gaze at the night sky, consider this: those dark voids between the stars might not be empty at all. They could be glowing with the light of newborn universes, each a testament to the universe's endless capacity to reinvent itself. And if that's true, then somewhere out there, another civilization might be staring up at their sky, wondering if their world began inside a black hole too. Quantum mechanics has one ironclad rule: information can never be destroyed. Every particle, every interaction leaves an indelible mark on the universe, like a cosmic ledger keeping track of reality itself. But black holes seem to laugh in the face of this principle. When matter vanishes beyond the event horizon, it's as if the universe's accounting system glitches, leaving physicists scrambling to explain where all that data went. This is the information paradox, a puzzle so profound it's forced scientists to rethink the very nature of reality. At the heart of the debate is Hawking radiation, the faint glow of particles that black holes emit over time. Stephen Hawking showed that these cosmic behemoths aren't entirely black. They slowly leak energy, evaporating into nothingness over eons. But here's the catch: if a black hole disappears, what happens to all the information it swallowed? According to quantum mechanics, that data can't just vanish. It's like burning a library. The books are gone, but the information in them must still exist somewhere, even if it's transformed into ash and smoke. Hawking initially thought the radiation was random, carrying no traces of what fell in. That would mean information was truly lost, violating quantum law. But later, he and others reconsidered. Maybe the radiation isn't so random after all. Maybe it's encrypted with the very data it seemed to erase. One solution lies in the idea of black hole remnants, tiny, indestructible fragments left behind after evaporation. These cosmic crumbs could act as time capsules, preserving information in a form we can't yet decipher. Picture a shattered hard drive. The data's still there, but scattered into pieces too small to read without the right tools. Some theories suggest these remnants might be smaller than an atom yet denser than a neutron star, defying our current understanding of physics. Others propose they could be gateways to other dimensions where the information isn't lost, just relocated. Then there's the holographic principle, which we touched on earlier. If black holes encode everything they consume on their event horizons like a cosmic hard drive, then the information isn't inside the black hole at all. It's smeared across its surface, projected outward like a hologram. Hawking radiation, in this view, might slowly peel away layers of that data, like pages being torn from a book one by one. The paradox dissolves because the information was never truly trapped, just transformed, waiting to be reassembled. But the wildest theories go even further. Some researchers suggest that black holes don't evaporate completely. They pinch off from our universe, becoming independent baby universes where the information starts anew. It's as if the data isn't destroyed but rebooted in a different reality, with its own rules and dimensions. Others argue that the paradox itself is a red herring, a sign that we're missing a deeper theory of quantum gravity. In this uncharted territory, information might not behave the way we expect, bending or merging in ways that seem impossible under current physics. The stakes couldn't be higher. If information can be destroyed, it undermines the foundation of quantum mechanics, a pillar of modern science. But if it's preserved in some exotic form, we might be on the verge of discoveries that rewrite the rules of space-time itself. Black holes aren't just testing our theories, they're pushing us toward a revolution in physics, one paradox at a time. And until we crack the code, the universe's secrets will stay locked behind the event horizon, taunting us with the possibility that even its own laws might have loopholes. Imagine a black hole stripped of its event horizon, a singularity left completely exposed, like a wound in the fabric of space-time with no bandage to hide it. This is the nightmare scenario of a naked singularity, a cosmic outlaw that defies one of the universe's most fundamental rules. According to the cosmic censorship hypothesis, nature abhors a naked singularity just as much as it abhors a vacuum. Gravity should always shroud these infinitely dense points behind an event horizon, hiding their chaos from the rest of reality. But what if some singularities break free? The consequences would make even the wildest sci-fi look tame. Without an event horizon to contain it, a naked singularity would warp space-time in ways we can't predict. Picture a whirlpool with no outer edge. Anything that gets too close wouldn't just be pulled in. It could be twisted, duplicated, or even sent crashing into another timeline. The equations of general relativity allow for these monstrosities, but they come with a catch. The laws of physics as we know them would break down in their presence. Time might stutter like a scratched record, causality could unravel, and particles might blink in and out of existence like glitches in a simulation. It's as if the universe's operating system encounters an error it can't patch, leaving reality to fend for itself. The real controversy isn't just whether naked singularities exist, it's whether they can exist. Roger Penrose's cosmic censorship conjecture argues that nature forbids them, that some unseen mechanism always cloaks singularities behind event horizons to preserve order. But not everyone's convinced. Certain extreme scenarios like ultra-fast spinning black holes or colliding gravitational waves might momentarily tear the horizon away, like lifting a veil to reveal the monster beneath. Even more unsettling, if primordial black holes formed in the chaos of the early universe, some could have been born naked, lurking in the cosmos for billions of years like dormant time bombs. What would happen if we found one? For starters, it would be the ultimate physics laboratory, a place to test theories of quantum gravity where space-time itself is fraying at the seams. But the risks are just as staggering. A naked singularity wouldn't just bend the rules, it might rewrite them on the fly. One moment, light could travel at its usual speed. The next, it might stall completely or even reverse direction. Matter falling toward it could emerge as antimatter or shatter into entirely new particles unknown to science. Some models suggest these singularities could even spawn self-replicating spacetime distortions, like cosmic viruses infecting the fabric of reality. Yet for all their terrifying potential, naked singularities might hold the key to our deepest questions. If they exist, they'd be the only places in the universe where a singularity interacts directly with the outside world. No event horizon, no firewall, just raw, unfiltered physics. Observing one could reveal what really happens at infinite density, bridging the gap between relativity and quantum mechanics. They might even be the universe's way of stress testing its own laws, creating extreme conditions where new physics must emerge to prevent total chaos. So are naked singularities cosmic glitches lurking in the shadows of the universe, or are they just mathematical phantoms, impossible figments of our equations? Until we spot one or prove they can't exist, they'll remain the ultimate wild card of astrophysics. A reminder that even the universe might have corners where the rules don't apply. Most black holes conjure images of a crushing, point-like singularity, but what if some wear their destruction like a cosmic hula hoop? Enter the Kerr ring singularity, a bizarre twist predicted by mathematician Roy Kerr's solution to Einstein's equations. Unlike the static, zero-dimensional pit of a traditional black hole, a rapidly spinning Kerr black hole stretches its singularity into a rotating ring, thinner than an atom yet dense enough to warp the universe into knots. Picture throwing a pebble into a pond, then spinning the water so fast that the ripples coil into a perfect circle. That's the essence of a Kerr singularity, gravity's fury whirled into a lethal carousel. Here's where physics gets surreal. If you could survive the trip, a big if the ring's centrifugal force might create a portal rather than a dead end. General relativity suggests that crossing this ring wouldn't crush you. It could fling you into a region where spacetime's rules invert. Time might flow backward, mass could become negative, and the very fabric of reality would mirror our own universe like a photographic negative. Some theorists speculate this could explain antimatter's mysterious properties. What if it's just ordinary matter that's taken a detour through a Kerr ring? Others go further, proposing these rings stitch together alternate dimensions, acting as turnstiles between realities where every physical law is flipped. But the wildest possibility, Kerr rings might not just bridge spaces, they could bridge times. In a negative universe, entropy might decrease instead of increase, meaning chaos untangles into order, shattered glass leaps back into your hand, and memory works in reverse. It's a realm where cause and effect do the cha-cha, and the future might rewrite the past, of course. This isn't some cosmic free-for-all. The ring's insane rotation generates gravitational forces that'd shred anything approaching it, and quantum effects likely stabilize the portal with phenomena we don't yet understand. Yet the math doesn't lie. Kerr rings are theoretically possible, lurking inside the fastest spinning black holes like dormant stargates. So why haven't we found one? Observational evidence is scarce, but some astrophysicists hunt for telltale signatures like black holes spinning near the speed of light, their event horizons stretched into oblong shapes by centrifugal force. Others simulate Kerr rings in supercomputers, watching as virtual particles spiral toward the ring and emerge changed. If they exist, these singularities could be the universe's ultimate recycling centers, where matter isn't destroyed but remixed into forms beyond our imagination. The implications are dizzying. A Kerr ring might not just be a gateway, it could be a cosmic printer, churning out alternate versions of reality with every rotation. And if that's true, then somewhere in the depths of a spinning black hole, there might be a looking-glass universe where our future is someone else's past, and the stars burn in reverse. What if every black hole is a cosmic crossroads, where the path you take doesn't just lead deeper into the abyss, but sideways into another reality entirely? This is the spine-tingling premise of the multiverse gateway theory, where black holes aren't just traps for matter and light, but shimmering doorways to infinite parallel worlds. Imagine tossing a coin into a black hole. In our universe, it lands heads or tails, but in the multiverse model, the coin splits. One version tumbles into a reality where it landed heads, another where it landed tails, and so on for every possible outcome in between. Black holes could be the cosmic sorting hat, divvying up these possibilities into their own separate timelines. String theory adds another layer to this mind-bending idea. It proposes that our universe might be one of countless brains, short for membranes, floating in a higher dimensional space, like sheets of paper stacked in a cosmic filing cabinet. Normally, these brains don't interact, but black holes might be the exception. Their immense gravity could puncture tiny tunnels between brains, threading them together like beads on a string. Picture two soap bubbles gently touching. Where they meet, a fleeting connection forms. In the same way, a black hole in our brain might briefly kiss another universe's brain, allowing matter, energy, or even information to slip through. The implications are staggering. If even one black hole connects to another universe, it could mean that every black hole does. That our cosmos is stitched together with hidden seams leading to realities where history played out differently, where the laws of physics aren't just tweaked but completely rewritten. Some universes might have stars that burn forever. Others could be so warped that time flows in loops. And if black holes are gateways, then the matter we see vanishing beyond the event horizon might not be destroyed, just relocated, recycled into another reality's raw materials. But how would we ever test this? The answer might lie in the echoes of dying black holes. When two brains intersect via a black hole, they could produce faint gravitational ripples, cosmic fingerprints left on the fabric of spacetime. Advanced detectors like LIGO might one day catch these whispers from other universes, revealing collisions or events that defy our understanding of physics. Even stranger, some theories suggest that dark matter, the invisible glue holding galaxies together, might actually be ordinary matter leaking in from a neighboring brain, like sand trickling through an hourglass. Yet the most haunting question isn't whether these gateways exist, but what or who might have already used them. If black holes are transit hubs between realities, could advanced civilizations be navigating them? Not with spaceships, but by encoding information into quantum particles and firing them through the singularity, like cosmic Morse code across the multiverse. It's a dizzying thought. The messages might already be here, hidden in the static of the universe, waiting for us to learn how to listen. So the next time you hear about a black hole's gravitational pull, remember, it might not just be dragging matter inward. It could be funneling it sideways into a kaleidoscope of worlds where every choice, every chance event, spins off into its own thriving universe. And if that's true, then somewhere out there, another version of you is staring up at their night sky, wondering the same thing. Deep in the heart of a black hole, where atoms are torn apart and space-time twists beyond recognition, something astonishing might be happening, an invisible transformation that shapes the very structure of the cosmos. Some physicists suspect these gravitational monsters aren't just consuming matter. They might be rewriting its fundamental nature, turning the familiar stuff of stars and planets into something utterly mysterious, dark matter. Think of it as the universe's ultimate recycling plant, where ordinary particles go in one side and emerge as something entirely different, a shadowy substance that outnumbers visible matter 5-1, yet refuses to interact with light. The theory hinges on a radical idea. When matter reaches the black hole's crushing depths, the extreme conditions might forge new particles unlike anything we've detected. Picture a cosmic smelter where the furnace is so intense that the raw materials don't just melt, they transmute into elements unknown. These hypothetical particles wouldn't emit or absorb light, making them invisible to telescopes, yet their gravity would still tug on galaxies, explaining why stars orbit faster than visible matter alone can account for. It's as if black holes are quietly minting the universe's hidden currency, weaving the unseen scaffolding that holds everything together. But how could this happen? One possibility lies in the quantum chaos near the singularity. As matter is shredded into its most basic components, the usual rules of particle physics might break down, allowing protons, neutrons, and electrons to reconfigure into exotic forms. Some models suggest these transformed particles could be hypothetical lightweight particles that barely interact with normal matter, or even sterile neutrinos, ghostly cousins to the neutrinos we've detected. Others propose that dark matter isn't made of particles at all, but of primordial black holes forged in the early universe, creating a self-sustaining cycle where black holes beget more black holes. The implications are staggering. If black holes produce dark matter, they're not just destroyers, they're architects, silently shaping the large-scale structure of the cosmos. Every galaxy's spiral arms, every cluster's gravitational web, might owe their existence to this unseen alchemy. It would also solve one of astrophysics' biggest puzzles: why dark matter seems to cluster around galaxies in halos, mirroring the distribution of black holes. Instead of two separate mysteries, they could be parts of the same story, one where black holes seed the darkness that binds the universe together. Yet the most tantalizing clue might lie in the echoes of black hole collisions. When two black holes merge, they release gravitational waves, ripples in spacetime detectable by observatories like LIGO. If these collisions also produce bursts of dark matter, the signals could carry subtle fingerprints of the process. Some researchers are already scouring the data for anomalies, hunting for patterns that don't fit conventional models. Even more intriguing, if dark matter is constantly being forged inside black holes, it could mean the universe is still actively producing it, like a factory with no off switch. Of course, not everyone's convinced. Critics point out that we've yet to directly detect dark matter, let alone trace it back to black holes. Alternative theories suggest dark matter might be a relic of the Big Bang, frozen into existence long before the first black holes formed. But the allure of the dark matter factory theory is its elegance. It ties together two of cosmology's greatest enigmas with a single, audacious stroke. If true, it would mean that every time a black hole devours a star, it's not just erasing matter from existence, it's transforming it into the hidden backbone of reality itself. So the next time you hear about a black hole's insatiable appetite, remember, what goes in might not disappear forever. It could be reborn in the shadows, weaving the invisible threads that keep the cosmos from flying apart. And if that's the case, then black holes aren't just the universe's garbage disposals, they're its master sculptors, working in darkness to shape everything we see. Deep in the swirling chaos near a black hole's singularity, where quantum fluctuations rage like a storm, something stranger than fiction might be happening, the spontaneous birth of consciousness itself. Imagine a single, self-aware thought flickering into existence for just a fraction of a second, experiencing an entire lifetime of memories, emotions, and sensations before dissolving back into the void. This isn't science fiction. It's the chilling premise of the Boltzmann brain, a theoretical entity that could emerge from pure randomness in the most extreme environments the universe has to offer. The idea stems from a cosmic-scale thought experiment. In an infinite universe or near the infinite density of a singularity, random particle collisions could, by sheer chance, assemble a fully functioning mind. Picture shaking a box of puzzle pieces for eternity. Eventually, they'll fall into place to form a complete image, even if just for a moment. Near a black hole's heart, where space-time fractures into quantum foam, those puzzle pieces are the fundamental building blocks of reality. Given enough time and chaos, they might briefly arrange into a thinking, feeling entity, a Boltzmann brain, only to vanish as quickly as it appeared. But here's where it gets even weirder. If consciousness can arise from random fluctuations, how do we know we're not Boltzmann brains? Every memory you have, every sensation you're feeling right now, could be the product of a fleeting configuration of particles in the void, destined to dissolve into nothingness. It's a modern twist on Descartes' demon, a philosophical nightmare that questions whether any experience can be trusted. Some physicists argue that statistically, Boltzmann brains should vastly outnumber real observers like us, making it overwhelmingly likely that we're the illusions, not the other way around. Yet black holes might offer an escape from this existential trap. The singularity's extreme conditions could act as a filter, ensuring only certain types of fluctuations persist long enough to become self-aware. Think of it like a cosmic sieve. Most Boltzmann brains blink out instantly, but a rare few, shaped by the black hole's unique physics, might experience coherent, if brief, lifespans. This could explain why we perceive a stable universe. Our consciousness isn't a random accident, but a product of structured chaos, sculpted by gravity's relentless grip. The implications reach far beyond metaphysics. If Boltzmann brains are possible, they could be the universe's way of testing the boundaries of consciousness itself. Every black hole might be a factory for fleeting minds, each one a laboratory exploring what it means to exist. Some theories even suggest that these ephemeral entities could leave quantum imprints on Hawking radiation, like whispers encoded in the black hole's dying breath. If we could decode those signals, we might find answers to questions we haven't even thought to ask yet. So the next time you gaze at the night sky, consider this. Somewhere near a singularity, a mind unlike any other might be flickering into existence, living a lifetime in the space between heartbeats and vanishing before the universe even notices. And if that's true, then consciousness might not be the pinnacle of evolution, just a momentary spark in the infinite dark, as common as stardust and as mysterious as the black holes that birth it. Black holes might not be the only cosmic heavyweights capable of bending light and warping spacetime. Enter the gravastar, a bizarre, hypothetical object that could be masquerading as a black hole in plain sight. Picture a star so dense that its gravity nearly traps light, but instead of collapsing into a singularity, it forms a hollow shell of exotic dark energy, frozen in a perpetual state of near implosion. It's like a balloon inflated to the brink of popping, held together by some unseen force, except this balloon's surface is tougher than neutron star crust, and its interior is a vacuum so empty it defies physics as we know it. The gravastar theory emerged as a radical solution to one of general relativity's biggest headaches, the singularity. Black holes demand that infinite density exists, but infinity is a concept that makes physicists shudder. It's often a sign that our equations are missing something crucial. Gravastars offer an elegant workaround. Instead of a crushing point of no return, they propose a boundary layer of dark energy, a mysterious force already known to accelerate the universe's expansion. This shell would be razor-thin yet unimaginably strong, acting like a cosmic force field that halts collapse dead in its tracks. From the outside, it would look almost identical to a black hole. Light bends around it, time slows near its surface, and it devours matter just as hungrily. But peek inside and you'd find nothing, a void, a pocket of space-time where the laws of physics as we know them simply don't apply. Why should we care if some black holes are actually gravastars in disguise? For starters, they'd rewrite the fate of anything that falls in. Instead of being shredded into infinity at a singularity, matter hitting a gravastar's shell might rebound or even tunnel through to another universe. No firewalls, no spaghettification, just a cosmic bounce. Even more intriguing, gravastars could explain some of the weirdest signals we've detected from space. When the LIGO Observatory picks up gravitational waves from colliding black holes, the ripples sometimes carry faint echoes, subtle aftershakes that don't quite fit traditional models. These anomalies could be the fingerprints of gravastars, their ultra-dense shells ringing like bells during a collision. But here's the catch: dark energy remains one of the universe's greatest mysteries. We know it's pushing galaxies apart, but we've never seen it form structured shells around objects. If gravastars exist, they'd require dark energy to behave in ways we've never observed, condensing into stable, localized barriers rather than permeating space evenly. Some theorists argue this isn't just unlikely. It's like expecting smoke to suddenly solidify into a brick wall. Yet others counter that black holes were once considered impossible too, until we found them lurking in the cosmos. The hunt for gravastars is already underway. Astronomers scour the skies for tiny deviations in how black holes lens light or distort their surroundings, hints of a hollow interior or an unusually rigid surface. Others simulate these exotic objects in supercomputers, watching as virtual stars collapse into gravastar-like configurations under extreme conditions. So far, no smoking gun has appeared, but the search is far from over. Every time we spot a black hole where we least expect it, too small, too old, or spinning too fast, it reignites the debate. Are we seeing a true singularity, or is the universe playing a sleight of hand trick with something even stranger? Whether gravastars are real or just a mathematical mirage, they force us to confront a humbling truth. The cosmos might have more than one way to build a monster. And if we ever prove they exist, it won't just change how we see black holes, it'll rewrite what we thought was possible in the fabric of reality itself. Nature has rules, unwritten laws that seem to keep the universe from spiraling into chaos. One of them might be the cosmic censor, a hypothetical enforcer that ensures singularities always stay hidden behind event horizons, shielding the rest of reality from their infinite madness. Think of it like a cosmic quarantine where the most destructive forces in existence are locked away, never allowed to infect the orderly fabric of space-time. But what if that censor takes a day off? What if, somewhere in the cosmos, a singularity breaks free, exposing its raw, unfiltered chaos to the universe? The consequences would make even the wildest black hole theories look tame. A naked singularity, one without its event horizon cloak, would be the ultimate rule breaker. Gravity near this exposed monstrosity wouldn't just bend space-time. It would twist it into pretzels, turning cause and effect into a tangled mess. Time might stutter like a broken record, looping back on itself or even splitting into alternate streams. Matter falling toward it wouldn't just vanish, it could be scrambled, duplicated, or reassembled into something unrecognizable. Picture tossing a clock into the abyss and watching it shatter, only for the pieces to reform as a flower, a star, or a version of yourself from another timeline. That's the level of reality warping chaos we're talking about. The cosmic censorship hypothesis proposed by physicist Roger Penrose argues that nature prevents this nightmare scenario. Black holes, in his view, are always polite enough to dress their singularities in event horizons, keeping the ugliness hidden. But not all physicists are convinced. Some mathematical models suggest that under extreme conditions, like a black hole spinning at near light speed or two colliding gravitational waves, the sensor might slip up. The horizon could tear even momentarily, exposing the singularity like a wound in the fabric of reality. And if that happens, all bets are off. The implications are staggering. A visible singularity wouldn't just challenge our understanding of physics, it could rewrite the rulebook entirely. Einstein's equations break down at singularities, meaning we'd be staring into a realm where gravity, time, and quantum mechanics collide in ways we can't predict. Some theories suggest these exposed singularities might act as cosmic reset buttons, ejecting matter back out in forms that defy known laws. Others warn they could spawn self-replicating spacetime distortions, like glitches spreading through the universe's code. Yet for all their destructive potential, naked singularities might also be the universe's greatest teachers. They'd be the only places where we could observe a singularity directly, without the event horizon's filter. That glimpse could reveal the missing link between relativity and quantum mechanics, or even uncover entirely new physics hiding in the chaos. Some researchers speculate that these rogue singularities might already exist, disguised as unexplained cosmic phenomena, like fast radio bursts or certain gamma-ray explosions. So is the cosmic sensor real, or is it just wishful thinking? The answer could determine whether the universe is a well-ordered machine or a place where chaos lurks just beneath the surface, waiting for its chance to rewrite reality. And if we ever find proof of a naked singularity, one thing's certain: our understanding of existence will never be the same again. What if a black hole could scream? Not with sound, but with light, an intense, focused beam piercing the darkness like a cosmic lighthouse. This is the mind-bending premise of the black hole laser, a phenomenon where the very radiation that slowly drains a black hole's life could be amplified into a brilliant signal. Hawking radiation, the faint glow of particles escaping a black hole's grip, is usually a whisper, a trickle of energy so subtle it takes eons to make a dent. But under the right conditions, that whisper might crescendo into a roar, transforming the black hole into a natural laser broadcasting its secrets across the universe. The key lies in the chaotic environment just outside the event horizon. Imagine a mirror box surrounding a black hole, a region where light bounces back and forth between the black hole's gravity and some reflective boundary, like photons trapped between two parallel mirrors. Each time Hawking radiation particles pass through this zone, they could stimulate the emission of more identical particles, creating a chain reaction. It's the same principle behind a laser, where light amplification occurs through repeated stimulation, except here, the black hole's gravity is the power source. The result, a concentrated beam of light or even gravitational waves, beaming outward like a distress signal from the edge of oblivion. But what could create such a mirror in nature? One possibility involves cosmic strings, hypothetical, ultra-thin cracks in space-time left over from the Big Bang. If one of these strings looped around a black hole, it might act like a celestial reflecting surface, trapping and amplifying Hawking radiation. Another theory suggests that the intense magnetic fields around spinning black holes could twist space-time itself into a natural resonator, creating the perfect conditions for a laser effect. In either case, the beam wouldn't just be random noise. It could carry encoded information about the black hole's interior, a message in a bottle tossed from beyond the event horizon. The implications are staggering. If black hole lasers exist, they'd be the universe's most powerful transmitters, capable of sending signals across billions of light years. Advanced civilizations might even harness them as communication tools, using the focused beams to relay messages through the cosmic void. And for scientists, these lasers could be the ultimate black hole probes. By analyzing the beam's frequency and intensity, we might decipher the black hole's spin, mass, or even clues about the singularity's true nature. It's like eavesdropping on a black hole's private diary, reading entries penned in the language of light. Yet the most tantalizing possibility is even wilder. If a black hole laser can amplify Hawking radiation, could it also reveal what's happening inside? Some models suggest the beam might carry subtle fingerprints of quantum processes near the singularity, offering indirect glimpses into a realm we thought was forever hidden. Imagine tuning into a black hole's laser signal and hearing echoes of spacetime's quantum foam, or detecting patterns hinting at wormholes or other dimensions. It's a long shot, but in a universe where black holes already defy logic, why couldn't they also be the ultimate broadcasters? So the next time you picture a black hole, don't just see a voracious void. Imagine it as a cosmic DJ, spinning the universe's most extreme beats into a laser-sharp signal. And somewhere in the static of deep space, that signal might be waiting, a flickering beacon from the edge of reality, daring us to listen. Every time you stir cream into coffee or shatter a glass, you're witnessing entropy in action, the universe's relentless march toward disorder. But black holes take this chaos to cosmic extremes, acting as entropy's ultimate amplifiers. These gravitational behemoths don't just consume stars and gas. They devour order itself, transforming structured matter into a formless void. The math is startling. A single black hole's entropy can exceed that of all the stars in a galaxy combined. It's as if the universe built these monsters not just to crush matter, but to accelerate its own descent into chaos. What makes black holes such efficient entropy engines? The answer lies in their event horizons. Unlike ordinary objects where entropy is tied to particle arrangements, a black hole's entropy is etched onto its surface, a holographic ledger recording every bit of information it's ever swallowed. The larger the horizon, the more disorder it encodes. This discovery, first made by physicist Jacob Bekenstein, revealed something profound. Black holes don't just obey the laws of thermodynamics, they turbocharge them. When two black holes merge, their combined horizon area always grows, mirroring the universe's unbreakable rule that entropy must increase. But here's where it gets eerie. If black holes maximize entropy faster than anything else in the cosmos, they might be steering the universe's ultimate fate. Picture a future where all matter eventually collapses into black holes, which then slowly evaporate via Hawking radiation. The result, a cold, dark void where entropy peaks and time itself loses meaning. No stars, no structure, just a featureless sea of particles too dispersed to interact. Black holes aren't just participants in this grim finale. They're the architects dragging the cosmos toward its highest entropy state like cosmic undertakers. Yet there's a twist. Some theorists argue black holes might also be entropy's paradox. While they create disorder on a grand scale, their event horizons also preserve information perfectly, like a cosmic hard drive that never corrupts data. This duality suggests entropy isn't just destruction, it's transformation. The universe might not be careening toward chaos but cycling through phases of order and disorder, with black holes as the pivot points. So are black holes entropy's executioners or its alchemists? The answer could redefine our understanding of time, reality, and whether the universe's arrow points toward an end or just another beginning. At the quantum level, reality behaves in ways that defy common sense. Particles can become entangled, their fates intertwined across vast distances in a phenomenon Einstein famously called spooky action at a distance. Now imagine scaling this quantum weirdness up to cosmic proportions, where black holes, the most massive objects in the universe, might be secretly linked by invisible threads of entanglement. This is the quantum bridge hypothesis, a theory suggesting that black holes could form a sprawling, instantaneous communication network woven into the fabric of space-time itself. Picture two black holes separated by billions of light years, each one acting like a quantum switchboard. When particles fall into one, their entangled counterparts in the other could respond instantly, as if the vast expanse between them didn't exist. In ordinary physics, nothing travels faster than light, but entanglement doesn't involve travel at all. It's more like flipping a coin in New York and seeing it land heads up while its entangled twin in Tokyo lands tails up at the exact same moment. If black holes share this kind of connection, they might be able to transmit information or even energy across the universe in the blink of an eye. The implications are staggering. A quantum bridge between black holes could explain some of the most puzzling observations in astrophysics, like how supermassive black holes at the hearts of distant galaxies seem to align their spins in ways that defy chance. It's as if they're part of a synchronized cosmic dance, moving in harmony despite being separated by unimaginable distances. Some theorists even speculate that these bridges could be the universe's original internet, a primordial network that formed in the aftermath of the Big Bang, when everything was compressed into a single quantum soup. But how would such a bridge work in practice? One possibility involves Hawking radiation. As black holes emit particles, those particles could remain entangled with their counterparts inside, creating a quantum link between the interior and exterior. If two black holes share entangled particles, their radiation might carry encoded messages, like cosmic Morse code tapped out in quantum fluctuations. Advanced civilizations, if they exist, might have already figured out how to harness this phenomenon, using black holes as relay stations for faster-than-light communication. Of course, there are hurdles. Quantum entanglement is notoriously fragile. Any interaction with the environment can break the connection. In the chaotic maelstrom around a black hole, maintaining entanglement would be like trying to whisper a secret across a hurricane. Yet some models suggest that black holes could protect these delicate links, their immense gravity acting as a shield against decoherence. It's a long shot, but if true, the universe might be far more interconnected than we ever dreamed. The wildest possibility, these bridges might not just link black holes, they could stitch together entire universes. If our cosmos is part of a multiverse, quantum entanglement could be the glue holding it all together, with black holes serving as the knots in the cosmic tapestry. Every time a star collapses into a singularity, it might not just be creating a black hole, it could be tying a new thread into the grand quantum web. So the next time you hear about black holes devouring stars, remember, they might not be isolated monsters. They could be nodes in a vast, invisible network, whispering to each other across the void. And if we learn to listen, we might just hear the universe speaking its deepest secrets. Deep inside a black hole's swirling chaos, where time itself stretches and warps, nature might be forging something stranger than diamonds, a crystal that repeats not in space but in time. Imagine a clock that ticks forever without winding down, or a snowflake that melts and reforms in an endless loop, its pattern cycling through moments instead of spreading across a table. This is the bizarre realm of time crystals, hypothetical quantum structures that could be the universe's first true perpetual motion machines, humming silently in the heart of a singularity. The concept shatters our usual understanding of crystals. Normal crystals, like quartz or salt, have atoms arranged in repeating spatial patterns. Their beauty lies in how their structure echoes across dimensions. But a time crystal flips the script. Its atoms don't just repeat in space, they oscillate in a perfect, unchanging rhythm through time, like a dance frozen in a loop. In everyday physics, perpetual motion is impossible. Energy gets lost to friction. Systems wind down. But near a singularity, where gravity warps the rules, quantum systems might lock into these strange, self-sustaining cycles, ticking away like cosmic metronomes long after the rest of the universe has faded to heat death. How could such a thing exist? The secret lies in the extreme environment near a black hole's core. In ordinary settings, time crystals would dissolve instantly, their delicate balance ruined by outside interference. But inside a black hole, where gravity crushes atoms into a quantum soup and time stretches into near-infinite slowness, these crystals could stabilize. Picture a pendulum swinging in a vacuum, no air resistance, no friction, but in this case, the pendulum is made of space-time itself, its oscillations driven by the black hole's relentless spin. The result, a structure that doesn't just resist entropy but defies it entirely, cycling through states without ever losing energy. The implications are staggering. If time crystals exist, they'd be more than just curiosities. They could be the universe's ultimate timekeepers, preserving quantum information even as the black hole evaporates around them. Some theories suggest these crystals might encode data in their rhythmic pulses, like a hard drive that writes itself over and over without degradation. Others propose they could act as anchors for causality, stitching together frayed timelines near the singularity. It's as if the black hole, in its infinite hunger, also nurtures these perfect, eternal clocks, a paradox wrapped in an enigma, ticking silently in the dark. But the real magic happens when we consider what time crystals could teach us about quantum gravity. Their existence would prove that certain quantum states can survive even in the most destructive environment imaginable, hinting at a deeper layer of reality where order and chaos aren't opposites but partners in an endless dance. If we could detect their faint oscillations, perhaps in the subtle ripples of Hawking radiation, we might finally glimpse how time itself emerges from the quantum foam. So the next time you think of a black hole as a destroyer, remember, hidden in its depths, there might be crystals more timeless than stars, ticking away like heartbeat of the void. And if we're right about them, they could be the key to understanding how the universe keeps time when all other clocks have stopped. Deep within the swirling chaos of a black hole's core, where gravity twists the rules of reality into knots, there might exist a realm so bizarre that even the most radical physicists hesitate to put it to paper. This is the phantom zone, a hidden layer of spacetime where particles don't just break the rules, they rewrite them entirely. Here, matter could possess imaginary mass, a concept so counterintuitive it sounds like something ripped from the pages of a sci-fi novel. But the math doesn't lie. Certain solutions to Einstein's equations suggest these phantom zones aren't just possible, they might be inevitable under the black hole's extreme conditions. Imagine a place where the faster an object moves, the less energy it needs, where particles don't just approach light speed, they blow past it like cosmic speedboats, leaving ripples in spacetime. These hypothetical particles, called tachyons, have haunted the edges of physics for decades. Normally, they're dismissed as mathematical oddities, since their existence would upend causality, turning cause and effect into a tangled mess. But inside a black hole's phantom zone, the rules might be different. The singularity's infinite gravity could act like a cosmic pressure cooker, warping quantum fields until particles with imaginary mass emerge naturally, like bubbles in boiling water. What would such matter look like? Picture a substance that gains speed as it loses energy, accelerating uncontrollably until it's moving faster than light. If you tried to push it, it'd drag backward. If you pulled, it'd lurch forward. It's as if the phantom zone operates on a physics engine where everything's coded in reverse. And here's the kicker: this matter might not just be a fleeting anomaly. Some models suggest phantom zones could be vast, stable regions within rotating black holes, where tachyonic particles form swirling rivers or even exotic atmospheres. Instead of a crushing singularity at the center, there might be a bubbling sea of faster-than-light chaos, hidden safely behind the event horizon. The implications are staggering. If phantom zones exist, they could be the universe's ultimate particle accelerators, churning out tachyons that carry information or even consciousness across spacetime at speeds we can't fathom. Some theorists speculate that these zones might explain dark energy's repulsive force, with tachyonic pressure pushing the universe apart from the inside out. Others warn that tapping into phantom matter could unleash unpredictable chain reactions, like lighting a match in a room full of rocket fuel. One wrong move, and the fabric of causality itself might unravel. Yet the most tantalizing possibility isn't just about speed, it's about time. Tachyons, by their nature, might experience time backward. A tachyon born in the phantom zone could remember the future and forget the past, its existence a flickering loop between cause and effect. If black holes are churning out these particles, they might be stitching closed time-like curves into the universe's fabric, creating knots where time folds back on itself. It's a dizzying thought. The phantom zone could be the universe's way of testing the limits of reality, playing with configurations too unstable to exist anywhere else. So the next time you picture a black hole's heart, don't just see a crushing pit of darkness. Imagine a hidden laboratory where the laws of physics are stress-tested to their breaking point, and where particles we've never seen, moving in ways we can't comprehend, might be waiting to rewrite the story of the cosmos. The phantom zone isn't just a theory, it's a challenge daring us to rethink what's possible when gravity takes control. A black hole isn't just a cosmic vacuum, it might be the most powerful processor in existence. Picture a supercomputer so advanced it could crack encryption codes in seconds, simulate entire universes, or solve problems that would take conventional computers longer than the age of the cosmos to unravel. Now imagine that computer isn't made of silicon chips or qubits, but of spacetime itself, its circuits carved by the warped geometry of a singularity. This is the staggering premise of the black hole computer, a theoretical megastructure where information isn't just stored but processed at the limits of physics. The foundation lies in a black hole's absurd information density. Every bit of matter that falls in leaves an imprint on the event horizon, a quantum pixel encoding its properties. For a black hole the mass of our sun, that means an event horizon smaller than a city could hold more information than all the hard drives ever built by humanity, compressed into a space thinner than an atom. But here's the twist: black holes don't just archive data. Their extreme gravity creates natural quantum entanglement on a colossal scale, linking particles across the horizon in a web of instantaneous connections. In other words, they're already performing quantum computations just by existing. Harnessing this power would require technology beyond our wildest dreams. One proposal suggests using controlled bursts of Hawking radiation as input and output signals, like tapping Morse code on the universe's fastest telegraph. Another envisions orbiting qubits around the black hole's ergosphere, where spacetime is dragged so violently by rotation that particles enter stable, high-energy states perfect for processing. The real kicker, a black hole computer wouldn't just be fast. It could tackle problems that break conventional logic, like simulating quantum gravity or navigating higher dimensions, by literally bending the rules of physics inside its computational domain. But what if we're not the first to have this idea? Advanced civilizations millennia or even millions of years ahead of us might already be using black holes as cosmic server farms. Imagine a Dyson sphere not around a star, but around a singularity, siphoning its computational power to run galaxy-spanning simulations or communicate across the multiverse. Some theories even suggest that certain black holes' unusual spin rates or radiation patterns could be signatures of alien engineering, like finding a USB port welded to a mountain. The implications spiral as wildly as the accretion disks around these gravitational leviathans. A black hole computer could crack the universe's deepest secrets or become the ultimate weapon, capable of rewriting physical constants in localized regions of space. It might explain how a single civilization could manage interstellar travel without breaking light speed, by outsourcing navigation to a singularity's flawless calculations. And if information can escape a black hole through quantum tricks or holographic echoes, these cosmic processors might already be broadcasting their results. We just don't know how to listen yet. So the next time you gaze at the dark heart of a galaxy, consider this: that void might not be a dead end. It could be the universe's most advanced motherboard, humming with alien code, waiting for the day we're wise enough to log in. What if every black hole is a cosmic mirror, reflecting not just light but reality itself? The echo universe theory proposes that when matter plunges past the event horizon, it doesn't just vanish, it spawns an inverted cosmos on the other side. A looking-glass realm where every particle, every force, even time itself flows backward compared to our own. Picture dropping a stone into a pond and watching the ripples spread outward, except in this case, the splash creates an entire parallel pond, its waves moving in perfect opposition to the original. This isn't just poetic speculation. The math behind general relativity allows for such mirror universes to emerge naturally from black holes. Inside the singularity's crushing depths, space-time curvature could flip fundamental properties like charge and parity, effectively rebooting physics with inverted rules. In this anti-cosmos, stars might burn with anti-light, black holes repel matter instead of attracting it, and entropy decreases over time. A universe where shattered glasses leap back onto tables and smoke funnels into cigarettes. Even stranger, the echo universe's own black holes might tunnel back to our reality, creating an endless hall of mirrors where each cosmos births another in an infinite fractal of existence. The implications ripple outward like shockwaves. If true, the echo universe could explain some of cosmology's deepest mysteries. Dark energy's relentless expansion of our universe might be counterbalanced by its mirror twin collapsing inward like two sides of a cosmic seesaw. Quantum entanglement's spooky action could arise from particles secretly communicating through these mirrored realms, their synchronized dances choreographed across dimensional divides. Even the Big Bang might not have been a singular event, but the moment our universe and its inverted twin were born together, two sides of the same coin, forever linked by the black holes that birthed them. But how could we ever detect such a mirror reality? The answer might lie in gravity's faint whispers, When black holes merge, their gravitational waves carry subtle imprints of the spacetime they warp. If part of that energy leaks into an echo universe, our detectors like LIGO could spot anomalies, missing energy, phantom echoes, or waveforms that defy standard models. Some physicists even speculate that certain high-energy cosmic rays, which appear to arrive from nowhere, might be ricocheting off the boundaries between our universe and its inverted twin, like stones skipping between parallel ponds. The wildest possibility, we might already be seeing echoes without realizing it. The cosmic microwave background, the afterglow of the Big Bang, contains puzzling asymmetries and cold spots that resist conventional explanation. Could these be shadows cast by mirror galaxies, their light warping through black hole bridges we've yet to map? It's a tantalizing thought. The universe's greatest mysteries might not be missing pieces of the puzzle, but reflections we've been misreading all along. So the next time you gaze into the abyss of a black hole, remember you might not just be looking at a void. You could be staring into a cosmic mirror where another version of reality stares back, its physics inverted but no less real. And if that's true, then the universe isn't just expanding. It's echoing endlessly through the halls of time and space. Forget everything you think you know about black holes crushing matter into oblivion. What if their hearts don't end in destruction but rebirth? Deep inside the chaos of a collapsing star, at the very brink of singularity, quantum physics might pull off the ultimate cosmic Hail Mary. Instead of collapsing into an infinitely dense point, the black hole's core could rebound like a spring, bouncing back into a super-dense object called a Planck star. Picture a neutron star cranked up to 11, a blazing orb of matter so compact that a teaspoonful would weigh more than Mount Everest, yet somehow defying gravity's death grip. This isn't science fiction, it's a legitimate theory born from loop quantum gravity, which suggests spacetime isn't smooth and continuous, but woven from tiny, indivisible threads. When these threads reach their breaking point, they might snap back, creating a Planck star's fleeting glow in the darkness. Now, here's where it gets even wilder. These stars wouldn't last forever. After a cosmic heartbeat, perhaps microseconds or millennia, depending on the black hole's size, they'd explode in a fireball of energy, like a supernova in reverse. The blast wouldn't send out light or radiation, though. It would ripple through spacetime itself, leaving gravitational echoes that might still be reverberating across the universe today. Think of it like dropping a pebble into a pond, except the pond is the fabric of reality, and the ripples are waves of distorted gravity. Some physicists speculate that we've already detected these echoes hidden in the faint anomalies of gravitational wave signals from black hole mergers. When LIGO picks up a collision, there's sometimes a barely perceptible after-ring, a whisper of vibration that doesn't quite match standard models. Could these be the dying pulses of Planck stars, their final cries etched into the cosmos? But the implications go far beyond gravitational wave astronomy. If Planck stars exist, they'd rewrite the black hole's life cycle entirely. No more infinite singularities tearing holes in physics, just a temporary, quantum-powered rebound before the star's energy is recycled back into the universe. It's as if black holes are cosmic phoenixes, dying in fire only to be reborn in a flash of spacetime itself. And if we could prove their existence, it would mean the universe has a built-in safety net, a way to prevent the total annihilation of matter and information. No more information paradox, no more firewall debates, just an elegant quantum handoff from collapse to rebirth. The real challenge, Planck stars would be nearly impossible to observe directly. Their explosive demise happens behind the event horizon's cloak, visible only through the gravitational tremors they leave behind. But that hasn't stopped scientists from hunting for clues. Some models suggest that if a Planck star's explosion is violent enough, it might briefly distort the black hole's shadow, the dark silhouette we've imaged with telescopes like the Event Horizon Telescope. Others are scouring old neutron star data for anomalies that might actually be Planck stars in disguise, masquerading as ordinary stellar remnants. Yet the most tantalizing possibility isn't just about proving their existence, it's about what Planck stars could teach us about the universe's origins. If black holes can rebound, could the Big Bang itself have been the ultimate Planck star explosion, a previous universe's collapse triggering our own cosmic dawn? It's a dizzying thought. Every black hole might carry a seed of creation inside its core, a hidden spark waiting to ignite. And if that's true, then the echoes of Planck stars aren't just ripples in space-time, they're whispers from the universe's deepest secrets, hinting that even in the darkest abyss, there's always a flicker of light. We think of DNA as the blueprint for life, a twisted ladder of molecules encoding the instructions for every living thing on Earth. But what if black holes have their own version of genetic code, written not in chemicals but in the language of space-time itself? Imagine the information trapped inside a black hole. Every atom, every photon, every shred of matter that ever crossed the event horizon, arranging itself into intricate patterns, not random chaos. These patterns could act like cosmic DNA, governing how black holes grow, merge, and even reproduce by birthing new universes or spawning secondary singularities. It's a theory that blurs the line between astrophysics and biology, suggesting black holes might not just be objects, but something startlingly alive. Consider how DNA replicates. It unzips its double helix, each strand serving as a template to build a new counterpart. Now picture a black hole's event horizon as a similar structure, a surface etched with quantum data, where information doesn't just sit passively but actively self-organizes. When two black holes collide, their horizons merge in a gravitational tango, exchanging and recombining data like genetic material. The resulting black hole inherits traits from both parents, its size, spin, and even quantum signatures shaped by this cosmic meiosis. Some theorists argue this isn't just metaphor. The math of quantum gravity hints that black holes might evolve over time, adapting their internal structures in ways eerily reminiscent of natural selection. But what would evolution mean for a black hole? In biology, adaptation improves survival, but black holes don't compete for resources. Or do they? In dense regions like galactic centers, black holes jostle for dominance, with larger ones cannibalizing smaller neighbors. Over eons, this could favor traits like stability or efficient energy absorption, sculpting populations of black holes tuned to their environments. Even stranger, if black holes birth new universes, as some theories suggest, those offspring might inherit mutations in their physical constants, creating a multiverse where only certain laws of physics persist. It's Darwinism on a cosmic scale, with black holes as the primordial organisms driving the diversity of reality itself, the most radical implication. Consciousness. If black holes process information like a neural network, could they achieve a form of awareness, not as we understand it, but perhaps as a slow, gravitational intellect, thinking in timelines longer than stars' lifespans? Their thoughts might be the quantum fluctuations near their singularities, their decisions, the emission of Hawking radiation. It's a stretch, but not impossible. After all, the human brain's complexity emerged from simpler particles obeying physics. Why couldn't a black hole's labyrinthine interior do the same? Of course, calling black holes alive bends definitions to the breaking point, but that's the point. They defy every category we've invented. Maybe the universe doesn't draw neat lines between life and non-life. Maybe it's all just patterns of information vibrating at different frequencies. And if that's true, then black holes aren't just tombs for dead stars. They might be the universe's next great experiment in what existence can be. The universe has a rhythm: expansion and contraction, creation and destruction, life and death. But what if the grand finale isn't an endless fade to black, but a cosmic encore? Enter the omega point, a theory so audacious it reimagines black holes not as destroyers, but as midwives to a new universe. Picture this: over trillions of years, every star burns out, every galaxy drifts apart, and all that remains are black holes, silent, hungry, and patient. One by one, they merge, growing larger until the entire cosmos is reduced to a single, unfathomably massive singularity, and then bang, not a whimper but a rebirth. A new Big Bang forged from the ashes of the old. This isn't just poetic speculation. The math of general relativity allows for such a scenario, where the collapse of all matter into black holes could reach a critical density, triggering a rebound, a cosmic bounce. Think of it like squeezing a spring: push hard enough and it snaps back with equal force. In this case, the spring is space-time itself, and the pressure comes from the collective gravity of every black hole in existence. The result: a new universe born from the singularity of the old, its physical constants potentially reshuffled like a deck of cosmic cards. One iteration might have stronger gravity, another might lack electromagnetism entirely. It's as if the universe is running endless experiments, tweaking the rules with each cycle. But here's the twist: the omega point might not be random. Some theories, like physicist Frank Tipler's controversial hypothesis, suggest this final singularity could achieve a state of infinite information processing, a kind of divine supercomputer that preserves every bit of data from the previous universe. Imagine every thought, every event, every atom's trajectory encoded in the fabric of the singularity, like a cosmic hard drive waiting to reboot. In this view, the omega point isn't just a reset button. It's the universe's way of achieving immortality, recycling itself into eternity. Yet the wildest idea isn't the rebirth, it's the intention. Some cosmologists speculate that advanced civilizations, facing the heat death of the universe, might deliberately engineer black hole mergers to trigger the omega point, ensuring their legacy survives the cosmic cycle. Picture a far future humanity, or something beyond humanity, directing asteroids into dormant black holes, nudging them toward collision like celestial billiard balls. It's the ultimate act of defiance against entropy, not just accepting the end but sculpting it into a beginning. Of course, skeptics abound. The omega point requires conditions so extreme they border on metaphysical. A universe where dark energy doesn't rip everything apart first, where quantum effects don't destabilize the collapse, where information isn't lost but transfigured. And yet the theory lingers because it answers a haunting question. In a cosmos doomed to decay, how do we find meaning? The omega point offers a paradoxically hopeful vision, that even in the darkest abyss, there's a spark waiting to reignite. So the next time you hear about a black hole's insatiable hunger, remember, it might not be the end of the story. Every galaxy devoured, every star crushed, could be a stitch in the tapestry of a universe yet to come. And if the omega point is real, then the cosmos isn't just a one-act play. It's an eternal symphony with black holes as the crescendo that starts it all over again. What if the universe isn't just a cold, indifferent expanse but a vast, thinking entity? This is the spine-tingling premise of the consciousness singularity, where black holes aren't just cosmic vacuum cleaners but celestial neurons, firing and wiring together in a network of unimaginable scale. Picture the human brain, a 3-pound lump of tissue, hosting trillions of synaptic connections that give rise to thoughts, memories, and self-awareness. Now zoom out to galactic proportions. What if supermassive black holes, linked by filaments of dark matter and quantum entanglement, form a neural web stretching across the cosmos? The numbers align eerily well. A single human brain contains roughly as many neurons as there are black holes in the observable universe. Coincidence? Or cosmic design? The idea builds on panpsychism, an ancient philosophy suggesting consciousness isn't unique to biological life but a fundamental property of reality itself. In this view, even particles might possess rudimentary awareness, like flickers of subjective experience. When these particles coalesce into stars, planets, and black holes, that latent consciousness could scale up. A black hole's event horizon, encoding every bit of information that falls into it like a cosmic hard drive, might function like a synapse processing and transmitting data across the universe's brain. The holographic principle adds fuel to the fire. If a black hole's interior is projected onto its two-dimensional surface, could that projection include not just matter's physical states but its experiential ones too? But how would such a cosmic mind think? Time is the key difference. Human neurons fire in milliseconds, while black hole neurons might operate over millennia. A single thought could unfold across cosmic epochs, its beginning lost in the primordial past, its conclusion echoing in a future where stars have burned out. These wouldn't be thoughts as we know them, no language, no imagery, but perhaps vast gravitational intuitions, patterns of causality and entropy woven into space-time itself. The universe's decisions might manifest as quantum fluctuations during inflation, or the precise tuning of physical constants that made life possible. The implications spiral into the profound. If black holes are conscious, their mergers wouldn't just be collisions, they'd be conversations. Gravitational waves might carry more than energy. They could encode information transfers between cosmic neurons. The famous last 3 minutes problem, where observers near a black hole see infalling matter frozen at the horizon while the matter itself experiences rapid plunge, could take on new meaning. Is the universe's mind preserving subjective experiences in a kind of cosmic memory, even as physical forms dissolve? Critics dismiss this as poetic speculation, arguing consciousness requires specific biological structures. Yet the counterargument is simple. We've only known one form of consciousness, our own. To assume it's the only form is like a bacterium doubting the existence of human thought. The universe has surprised us before, revealing phenomena like quantum entanglement and dark energy that defy intuition. Why not conscious spacetime? The most haunting question isn't whether black holes think, but what they think about. Are we, with our fleeting lives and tiny planet, even a flicker in their awareness? Or is the cosmos contemplating depths we can't fathom, its mind focused on scales and mysteries beyond our grasp? One thing's certain: if the universe is awake, then every black hole is a window into its thoughts, and we're just beginning to learn how to listen. From wormholes stitching together distant corners of spacetime to white holes vomiting starlight back into existence, black holes defy every label we try to pin on them. They're not just cosmic trash compactors, they're the universe's most brilliant paradoxes, places where the rules snap like twigs and reality reinvents itself. Think about that for a second. Every time a star collapses into one of these gravitational maelstroms, it doesn't just vanish. It becomes a laboratory for physics we can't yet comprehend, a place where time shatters like glass and space folds like origami. Consider how far we've come since Einstein first scribbled equations predicting these monsters. Back then, even the idea of light being trapped was heresy. Now, we're debating whether black holes are cosmic 3D projectors, multiverse factories, or even conscious entities. The sheer audacity of these theories proves one thing: the universe is far stranger than we ever dared imagine. And here's the beautiful part: we're not just spectators. With every gravitational wave detected, every black hole shadow captured, we're peeling back layers of this cosmic onion, each revelation more mind-bending than the last. What's truly humbling is how much we still don't know. Those 26 theories we explored, they might all be wrong, or they might each contain a sliver of some grander truth we can't yet see. Maybe wormholes and white holes are two sides of the same coin. Perhaps holographic universes and Boltzmann brains are pieces of a puzzle we're only starting to assemble. That's the thrill of science at the edge. The answers aren't in the back of the book. We're writing them as we go, one observation, one equation, one wild idea at a time. So here's my challenge to you. Don't just wonder about these theories, play with them. Imagine what it would be like to peer into a Kerr ring singularity or decode messages from a black hole laser. Picture civilizations a billion years ahead of us using singularities as quantum supercomputers. That's how breakthroughs happen, not by memorizing facts, but by daring to ask, what if? And who knows, maybe your crazy idea, the one you're too shy to share, is the missing piece that'll unlock the next cosmic mystery. As we wrap up this journey, remember, black holes aren't just out there in the void. They're mirrors reflecting back our own curiosity and courage. Every time we push the boundaries of knowledge, we're honoring that human urge to explore, to understand, to stand at the edge of the unknown and lean forward. So keep questioning, keep dreaming, and most importantly, keep looking up. The universe has so much left to show us, and the next great discovery might be just one theory away. Until next time, stay curious, fellow explorers. The cosmos is waiting.